we would like to thank and acknowledge our sponsors, DC3 Dreams and Boyce Astro. DC3 Dreams provides high-end observatory automation and web-based multi-user remote imaging. The AAVSO net observatories use DC3 Dreams ACP Expert for the Bright Star monitors and other programs. The AAVSO Photometric All Sky Survey project, also known as APAS, has used ACP Expert's AI scheduler to automatically acquire over 500,000 star fields, hands-off, at a rate of 1,000 square degrees per night. This has resulted in photometry for over 128 million objects in about 99% of the sky. The Boyce Research Initiative and Education Foundation provides online astronomy education, observatory resources, and research experiences to students, student teams, and schools in order to learn how to perform observations, conduct research, and publish their results in scientific journals, such as the Journal of the AAVSO. Please do check out their webpage to learn more about their work. Okay. Now, today's instructor has been an observer of variable stars since his high school days, when he independently discovered Nova Cygni. As an avid visual observer, he wrote a book called the Handbook of Binocular Astronomy, the contents of which are available not only in print form, but also on his website, starman.co.uk. His primary fascination is starbirth, so it's only natural that he's become a real expert on young stellar objects, or YSOs. He's been the leader of the AAVSO's Young Stellar Objects Observing section ever since its inception, and has produced a set of exceptional resources for the group, including an online target database and a very well-written newsletter. You can find those resources by going to the YSO Observing Sections page on the AAVSO's website. Now, today, he's here with us to teach us all about the different types of young stellar objects and their variability. So I recommend that you get ready to take notes, and we give a warm welcome to the YSO expert himself, Michael Poxen. Uh-oh, is Michael still with us? No, he is not. All right, hang on everyone while I reach out to Michael and see if we can get him reconnected. Apologies for this. Apologies for the technical difficulties, everyone. It seems that Michael is having trouble with his internet connection. While I'm attempting to get reconnected with him, just hang on. If this goes on for another 5 minutes, then maybe we'll do a tour of the AAVSO site or something like that. Oh, and there we go. Hello, Michael. How is your connection?
Oh, lovely. I'm so glad. Right. Would you like me to share now?
Yes, please.
Okay, let's just make that screen. Okay, can everyone see the zoo?
Yep, looks good.
That's good. That's lovely. Right. Well, I promised you all a visit to the zoo, and that's where you're going to get. It's not going to be a visit to London Zoo, which is what we see here, but it's going to be a visit to the zoo of various types of young stellar objects, or YSOs. However, this picture of London Zoo I haven't just kind of put it up for sort of national pride. It's actually related to YSOs. Then you might think, how can the London Zoo possibly be related to young stellar objects? Well, it is, because I believe London Zoo was built in about the 1920s or the 1930s. But before that, and in fact, even still today, it's known as Regent's Park. And of course, at those times, it was right on the outskirts of London, if not downright outside. So the skies were quite dark. And in Regent's Park lived a man by the name of John Russell Hind. Some of you might have heard of him, you might have heard of his Crimson Star. He also discovered Geminorum. So this is John Russell Hind. Sorry, there we go. 1823 to 1895. As you can see, he's a thoroughly respectable Victorian gentleman. Very Victorian, because he discovered an asteroid and named it after the dear old Queen. I'm sure that had nothing whatsoever to do with him being made a member of the Royal Astronomical Society. But he did. He searched for asteroids, and of course he was searching along the ecliptic. And in one of these searches, he found our dear old star T Tauri, which is the very first, as far as I know, the very first YSO to be discovered. When he discovered it, it was 9th magnitude. But by the end of the century, you can see here, it had faded to the 14th magnitude, where it has never been, as far as I know, ever since. It shortly came back up to about magnitude 10, which is kind of where it is now, really. When stars form, about 60% of the time, they form as non-single stars. So the sun is slightly an exception. And T Tauri is no exception to that method of formation, because it's a double star, possibly even a triple star. What makes a T Tauri star is largely its mass. Any star with a mass less than about 2.5, 3 times that of the sun is going to be a T Tauri star. Any more massive, and we'll have a little look later. The nebula that you can see in the bottom right-hand part is NGC 1555, which is one of the two nebulae which are called Hind's Variable Nebula. The other one, of course, is the famous one in Monoceros, which illuminates another YSO, Armand. But in this case, the nebula varies along with the star. At the moment, the star is pretty bright. It actually largely blots out the nebula, so the nebula is not really easy to see at the moment. But T Tauri itself is also enmeshed in a bit of nebulosity, which you might be able to see just around here, is the actual NGC 1555. Now, what I've done with this picture is I've overlaid some details from the there we go. Some details from the 2MASS point source catalogue. 2MASS is the 2 micron all sky survey. So it's looking for sources of infrared radiation. Now, some of these sources, for instance, this one up here, you might be able to see a tiny red circle there in front of the star, can be identified with actual visible stars. Obviously, we've got T Tauri itself here, but all along this nebula are lots of other sources of infrared radiation, which could well be forming stars. They could also possibly be bow shocks from T Tauri itself, because all these stars have what we call strong stellar winds. They're putting out sort of quite a bit of radiation. But to be absolutely clear, what really defines T Tauri star is its low mass. So 4.5 billion years ago, the sun was a T Tauri object. And I just have visions of alien astronomers 4.5 billion years ago watching the star form. And now, of course, it's us. So that's the basis of T Tauri stars, what they are.
Michael, I just want to interject real quick. I'm getting a little bit of interference in your audio. Do you have the correct microphone selected right now?
I do, yeah.
Okay. Well, I'm not quite sure what to do about it then if the correct one is selected, except for just if you could speak up maybe a little bit, that might help you be louder than the interference. We'll see. If you're speaking right now, we can't hear you.
Can't hear me. Oh.
Oh, now I can hear you.
Ah, okay. So is there a bit of a time lag?
As far as I know, there is not. You do sound clearer right now. You cut
Okay.
out for a bit, but now you're clearer.
Okay. Oh, good. Oh, you had me worried there for a minute. So yes, we've got T2 right here, varying roughly between magnitudes 10 and 10.8. It's going down a little bit here. It doesn't usually get that faint. So it does vary. It doesn't vary an awful lot. As a rule, I have to say as a rule, because there are always going to be exceptions. So as we can see here, one of the main things is that T Tauri stars are fairly low mass and also low luminosity. They tend to be what are called late spectral types. Occasionally spectral type F, usually G, K, or M. So they're orange to reddish kind of stars, not terribly luminous. The one thing that does mark them out is the fact that they have the element lithium in absorption. So it's in the upper layers of the star's atmosphere. And there's very good reason for that. Lithium is destroyed at temperatures above 2.4 million degrees Kelvin. So anywhere near the center of the star, where obviously it's hotter, and you don't find lithium. So we can say that lithium is a signature of youth in stars. Something else that marks, in fact, all young stars generally, is they are fast rotators, because they haven't long actually formed out of the parent gas cloud, which is not stationary. Everything in the universe is moving, and gas clouds are no exception. So that will all condensing out of the gas cloud will always tend to make the star rotate, and rotate quickly to begin with. The sun was probably rotating at this sort of speed again about 4.5 billion years ago. We're talking hours really, up to a few days. Obviously now at the moment the sun rotates in about 25-26 days. So as stars age, they slow down in terms of rotation. It's important to note, and this is the stage where I want to say, yes, we are going to look at the zoo, but we're going to look at the zoo in terms of behavior of stars, not so much the typology. So T Tauri stars aren't always necessarily going to vary as the one you see here. Some of them aren't going to vary as much. Some of them are going to vary an awful lot more. And I think it's the awful lot more ones that we're really interested in. Most of the light and the radiation that we see coming from very young stars, because obviously they are not yet hot enough in their cores to start fusing. Most of the light output we see is by gravitational energy, because the stars are contracting. So this is a general, very idealized picture of what a young forming star probably looks like. But we've got all these things to consider. There is not usually just one cause for variation in these young stars. So we've got the fast rotation here. Our baby star is rotating very quickly. This obviously can lead to star spotting, because fast rotation tends to be associated with a strong magnetic field, which tends also to be associated with star spotting. So as the spots rotate across the star, they can produce one element of the variation. Generally, these aren't very large kind of variations, but the star is also putting out stellar winds, putting out radiation, which can sometimes collide the circumstellar disk here. We've got material in the circumstellar disk, which can be dust, gas. It can be small pebbles like this, and obviously over time the small pebbles grow into rocks. The rocks grow into bigger rocks. The bigger rocks eventually can grow into planets. This usually takes place in the outer edges of the circumstellar disk. And we've also got what's called the bipolar outflows. These come because we have lots of material falling in towards the star, but it can only accommodate so much. So after a time, what you will get is you'll get the excess material that's coming in. It can't go back out because that's the very direction. That's the last direction it can go. So it takes the path of least resistance and goes out at points completely opposite to where all the stuff is coming in, and that is through the poles. And the bipolar outflows here can also go on to initiate further bursts of star formation elsewhere in what I will call the stellar ecosystem. It's quite a good choice of words because these aren't isolated. The individual star might be isolated, but it's in the theatre of creation, if you like. There's lots of other gas around it. There's lots of other interstellar material around it. So we have to think in terms of a sort of an environment rather than isolated objects. So let's just have a quick look at T Tauri stars generally. We can usually divide them into two broad types. There's what we call classical T Tauris or CTTs. What marks them out is the fact that they have a circumstellar disk. We also have the weak T Tauris, which have a very weak circumstellar disk or no circumstellar disk at all. They're both interesting from various points of view, but we can break these down. We can break the classical T Tauri stars down into sort of three types. There's the general type, like T Tauri itself, and it's got all these contributing factors to the variation. We've got bipolar outflows, we've got star spotting. T Tauri probably shows a bit of star spotting. We have interaction with the disk, both stuff going out into the disk and stuff falling in from the disk onto the star. And we have clumping in the disk, which we'll look at a bit later, but that's a very big contributing factor, especially to when the stars fade, because we find that rather like an eclipse, if the circumstellar disk and the star are tilted nicely from our point of view, some of the larger clumps can come between us and the star and thus make it fade. So we have our general T Tauri stars, but they can further be kind of subdivided into two other types. Now, I want to emphasize I would like to think of these as they are types of variation rather than necessarily types of star. But if for the moment you think of them as types of stars, because we're going to categorize them with various terms, I actually want to start off with the fluors. Now, basically what a fluor is, it's when large amounts of the circumstellar disk funnel down onto the star. It's a sort of a download of material, if you like. They're named after a star called Fu Orionis, which I think it was 1937. Before that, it was just a 16th magnitude star, so a pretty faint star. And over the course of a year or two, it rose up from magnitude 16 up until about magnitude 9. And that happened in 1937, and it's only about magnitude 10 now, so it's taken all that time to fall by 1 magnitude. They used to be thought of as very slow novae. Obviously, they've got absolutely nothing in common with novae at all, other than if you look at the light curve. But even then, it's an extremely slow nova, really. We're talking about in terms of how much material gets dumped onto the star, about 1/10,000th of a solar mass per year. Now you might think, well, 1/10,000th, that's a very small number. Well, yes, it is, but it's not a very small number when compared with the actual mass of the sun. So 1/10,000th of a solar mass is an awful lot of mass per year. Like the next type of YSO we're going to talk about, these stars, these fools, have what are called inverse P Cygni spectra, or profiles in their spectra. Really, all that means is if we think about P Cygni itself has got nothing to do with YSOs. But what happens in its case, it shows that very large amounts of material are streaming off the star into space. Well, here we've got the inverse happening. So we've got all the material not streaming off the star, but streaming down onto the star from the circumstellar disk. We haven't really seen any fool erupt more than once. And that's probably because, in general, for the same broad reason, we don't see novae explode more than once. That's simply because we don't live long enough. We think that a T Tauri star will go through a full episode. This is why I want to think of them as different behaviors rather than necessarily different types of star. We think that a T Tauri star, in fact, like the sun, all that while ago, go through a full episode several times in their sort of formation history. But obviously, the formation history takes millions of years, so we haven't really been around long enough yet to actually see this happen more than once. However, if we come to another group, which are the YSOs, which also show this inverse P Cygni profile, i.e., stuff is funneling down from the circumstellar disk onto the star, they're similar, but they happen on a rather quicker time scale. So rather than take years and years and years, decades to rise and then fall, these take months or just a few years. However, literally a couple of weeks ago, I had an email from one of the YSO section members, John Pickett, who I hope is here today, who looked at a star called V347 Aurigae. And what's happened there is it's like an XOR outburst. Think of them as outbursts. But instead of taking months, it just took a few days. And in fact, the whole episode was over, I think, in about a week. And the interesting thing about V347 Aurigae is that with the fools, we think, and with the XORs as well, the downloads are not periodic. But in the case of this particular star, it is. Apparently, it's shown these outbursts about twice a year. So whether this is a difference in kind or a difference in degree, I don't know. The fact that it's more regular would tend to indicate, actually, that we might be looking at a completely different type of star here, a completely different type of behavior. Obviously, time and observations are what we need in order to find out. So that's quite a lot of the sort of T Tauri zoo, if you like. The weak T Tauri stars are interesting, not necessarily for the same reason, but because we have a decoupled circumstellar disk, it's gone. Maybe it's been absorbed into a protoplanetary system, and we might have clumping there. So so we've got forming planets possibly going on. This also tends to happen with the slightly greater mass stars, which I now want to talk about, which I call Hades, because they stand for Herbig. George Herbig was a great friend of the AAVSO, and he studied these stars, which are of types A and B, and they show strong emission. So for that reason, they're called Hades. I call them Hades anyway. They're very like T Tauri stars, except they're more powerful and more luminous. So yes, they are still very young stars. Like T Tauri stars, they show an infrared excess. That's an excess of infrared radiation from the circumstellar disk. That's why we get the infrared excess. They also show strong stellar winds, as do the T Tauri stars. And again, they have evidence of clumping in the circumstellar disk as well. And all these things go to provide sometimes very complicated light curves. How they differ from the T Tauri stars is, as I said earlier, the mass. They have to be more massive. And also, we sometimes, or in fact, we often find that they're not attended by nebulae. In virtually every case, T Tauri stars are involved with nebulae, either bright or dark. These ones can be what you might call naked. There is no nebula material visible near them, and they're also hotter. Spectral types B and A, as a rule. Sometimes they might get a little bit cooler than that, and they often show very deep fades. We'll see in a minute that, in fact, sometimes so can the T Tauri stars as well. What they don't show is any rotational variability due to star spotting. Now, whether that's because for some reason they don't spot, or what is more likely, because the actual surface is going to be brighter, the star spots simply aren't visible because there is there just isn't the contrast there. So that's how they differ, but they're all young stars. This is the important thing. Right, I just want to introduce you to one of my friends. This is B730 CVI. This is one of these Hades. It's a hot star. Varies between about magnitudes 12 and 16. But here we've got a little bit more of a kind of regular variation going on, or semi-regular at least. But I don't think they've got anything to do with semi-regular variables, other than the fact that they show a bit of semi-regular variability. Semi-regular variables are all hot, all cool, very, very old stars, and obviously these are very, very young stars. So yeah, we can see here there's a sort of a period, and it goes all semi-regular up here, and going on, it simmers down again into about a period here of about a couple of weeks, something like that. But earlier than that, it's gone through all sorts of fun. Here, it's down to magnitude 15.7, and I know it's 15.7 because that's my observation, which is actually, as far as I know, it's the faintest ever recorded on this star. The other observation here, up here, this is at 14.2. And I know that's 14.2 because that observation was made by Mike Simonson, who sadly died not so long ago. But we stayed in touch quite a bit. And that, I think, was probably either the day before, it might even have been the same day. So 14.2 to 15.7 in the space of a day. So there's something serious going on here. And again, we can see there are quite deep fades here. We think what's happening is this star is probably forming a system of planets, and the material that's going on to form the planet or planets has come between us and the star. It's cut a large amount of the star's light off, so it's made it fade very, very deeply here. Now, why I think we have the 14-day period is there could well be another forming planet in the system, much closer in, which has only taken 14 days to go round. And again, every time it comes round, it comes between us and the star, but it might not be quite so big, so it's not cutting off quite enough light. So that's why we get this slight this rather more slight variation here. So this is all good stuff for the observer. Right, I just want to concentrate on a couple of stars now. This you already. Now, if you just think back to the general picture of the light curve of T Tauri earlier, this is how this star was varying. I mean, if the truth be told, a little bit boring, I suppose, certainly from the visual observer's viewpoint, varying over only about half a magnitude in these slow waves. Very interesting area of the sky. But Up until a few years ago, SU Origi, I say, nothing too much to write home about. An interesting YSO, but things happened over the past few years. What I just want to direct your attention to are again these are infrared sources. There's a lot around here. This is another YSO, by the way. This is AB Origi. This is SU here. This is the one we're talking about. But as you can see, AB Origi has got lots of nebula material around it, lots of infrared sources. It's actually visible entirely with binoculars. You don't even need a telescope for this one. But what's really interesting is this line of infrared sources here. This one here is also interesting. This is another YSO here. This is GM Origi. The AAVSO have just recently put out an alert to follow this one because it's being studied by the Hubble Space Telescope. But the interesting thing, as I say, is this line here. Now, whether something happened in this area in the past, say a really strong bipolar outflow, as we saw earlier, and that's gone along this track and it's kicked off lots of other star formation here, because we can't see stars here. So obviously, whatever is causing this infrared emission isn't bright enough to shine yet. So very, very young sort of protostars, I suppose. These two stars here, AD and SU, have what's called common proper motion. So, I mean, they're not technically a double star. They're not going round each other, but it looks as though they were both created at the same time in the same general area, because they're traveling together through space. What happened to SU Origi was so interesting. This is 2018. I was due to give a talk actually at the AAVSO meeting at Warwick University, and literally a week, it might not even have been that much, before I was due to give this talk, I had an email from I think it was Bart Stales in Belgium. And he said, I think you ought to take a look at SU Origi. And I did. And it was very, very weird because, as I said earlier, it normally varies between about magnitude 9 and 9.5. And here it is down at magnitude 11 visually. It's completely unheard of with this star. If you look at old records, it will give its range in light as 9 to 9.5. So where on earth is this coming from? So in fact, I changed the subject of my talk, which was originally going to be about another one of my favorite stars called V1117 Hercules, to SU Origi instead. And it's really interesting here, if we look at the variations across, a kind of range of wavelengths. This is visual. And as you go up the diagram here, you're getting into ever longer wavelengths. So, we're talking near and far infrared. And it's interesting. This is one reason why visual observations are useful. It's interesting that the sort of visual minimum here is very, very deep. It's much deeper than anything else. So whatever is causing this variation, it's probably solid material, because up here, we've got all the infrared areas, and they are not affected at all by whatever has caused this. In fact, if anything, they've got slightly brighter. So we've probably got a circumstellar disk here going on. It's doing its usual stuff. It's getting energy from the star. It's warming up and it's radiating in the infrared. But in the visual, so and the slightly longer wavelengths, something is definitely going on. And it's anyone's question exactly what. As I said, we've never seen this happen before, so this is a kind of a one-off. Of course, it might not be a one-off because these stars take a long time to form in human terms. This could well have happened 400 or 500 years ago, and we know nothing about it. But for the moment, let's assume that this is a one-off. So something is causing this that isn't part of your regular T Tauri variation. So again, we have a T Tauri variable but not necessarily with T Tauri type changes in light. This is actually more like the fading of the last star we looked at, right down to 15.7 kind of thing. So it's a very deep fade. And staying in Auriga, not far away, RW Auriga. This is a friend of a load of observers. It's been known for quite some time. Most of the time, it varies between about 10 and 11 and a bit, as you can see, going on here. And all of a sudden, 2011, we're what on earth is going on here? It hasn't done this before. I think it might have done it in about 1890 or something like that. If I think someone might have researched some of the old photographs. But here it's gone right down to, well, almost magnitude 14. I'm also involved in the sequence team as well. And in fact, at the time, I had to make some additional comparison stars because it actually faded below the level of the chart I was using. So this is very, very peculiar. This is from a paper by Joey Rodriguez, who is a very good, again, he's a very good friend of the AAVSO. I've met him at a couple of meetings, and he's always interested to have AAVSO observations of YSOs. And you can see how much he uses it because all these black dots are AAVSO observations. So never be in doubt that the professionals value our observations. Of course they do. So RW Auriga, again, it was thought of as being a T Tauri star. It's a low mass object, so technically that would make it a T Tauri star. Its variations are a bit more interesting or exciting than those of T Tauris. You know, it varies a bit more and a bit faster, but it certainly hardly ever does this. So again, this is like one of those Uxor things, like the sort of high mass stars with a very deep, fairly short minima. So again, yeah, we've got another one happening here, and I think another one also happened in 2018, the same year of the SU Auriga fade in the previous one. So what on earth is going on? Well, various people have had a look at this, and it turns out that RW Auriga is a double star. To show you on this strange diagram here, here's the main star, here's RW Auriga A, here's RW Auriga B. They're separated by about 200 AU. They only appear as a single star to us. They're too close together. But again, we've got to consider not just the stars, but the whole ecosystem, the whole stellar ecosystem, the entirety of the surrounding environment, and anything that can give rise to this strange behavior. Yeah, so the previous deep fade we saw on this star was 1890. So well over 100 years between these two deep fades. So there's a lot going on in the system. We don't just have the two stars, we have all the circumstellar material, we have the surrounding gas and dust farther out, we have any clumping that might be going on, forming planets. But our companion star, here B, the less massive star, is on a wildly eccentric orbit. And it appears what happens is, on this occasion, it came too close to the main star. It disrupted its circumstellar material, and it's basically flung it out into space. So it's again, it's anyone's guess what's actually going on there. And we think this big arc of material, you can see how big it is, has probably eclipsed the main star, which has given rise to these deep fades. And also the fades have been observed across wavelengths. And usually what that means, that's a signature of solid matter. So almost certainly what's happened here is any forming planets that there were here have been, if you want, deformed. They've been broken apart. So what we have here is a sort of a debris disk rather than a circumstellar disk. Well, in fact, we've got both. So a very, very complicated part of the sky. Various other elements have been found in RW Aurige's atmosphere, such as iron, which we think came out of the destroyed planets. And in fact, a couple of years after the fade, there was a paper written on this, and the paper predicted further fades, and lo and behold, there were further fades. I'll say that one in 2018. So to close, what you really have to bear in mind is we're not really so much talking about different types of star, we're talking about young stars that can show different types of behavior. And that's where we get the traditional sort of subsets like the UXORs and the FUORs and the HABEs and all the rest of them. So really what I want to try and impress is these are behaviors rather than necessarily different types of star. In some cases, you know, they are going to be different types of star, but really the sort of bottom line is what we're looking at is behavior rather than actual typology, if you want to think of it like that. So yes, if there are any questions, we can try and answer them. I'll stop screen sharing there.
Okay, great. Thank you so much, Michael. That was an excellent presentation. Okay, I see that we do have a couple questions already, so let's go to those. First of all, Andrew Corkle asks if there are any nice YSOs that do not fade fainter than 7th magnitude, because Andrew would like to do some visual binocular observing of YSOs.
Yes, well, in fact, as I said earlier on, that star we were talking about, AB Aurigae, that varies between magnitude 7.3 and 8.5. So, in fact, I started observing that with binoculars way back in the 80s, I think, because I think that's all I had at the time. There was a society actually run called the Binocular Sky Society, which was devoted entirely to the binocular observation of variable stars, and this is one of the stars on the program. But again, if we look back to that photo, it actually forms a Y double star with the other one we were talking about, which is SU Aurigae. That one's a bit fainter, so you might need slightly more powerful binoculars. Say something like, I mean, 10 by 50s are fine for AB Aurigae because that, you know, that's bright. Something a bit bigger if you want to get SU as well, or you know, or a very small telescope. So yes, there are quite a few. I mean, AB Aurigae is the brightest one. Usually, I mean, there are plenty that don't get as faint as 16th magnitude. That's just a particularly interesting one.
Great. Well, thank you. I've just written down those designations because I don't think that Andrew will be the only one going out and starting to observe YSOs and binoculars.
Well, in fact, if you go to my website, that is the YSO section of my website, not the AAVSO sort of version of it. Mine contains sort of a search box, and you can search by brightness. So you can search that you only bring up bright YSOs.
Excellent. I remember that page. I'm going to drop a link to that right in the Zoom chat here so that people can access that. There we go. That's the website that Michael was just talking about.
That's the one, yeah.
And while I'm at it, I'm also going to put a link to the AAVSO's Young Stellar Object page, which Michael put together, which has a lot of other great resources linked in the sidebar on the right where it says YSO pages. And yeah, that's a great list.
I think from there you can also get a link to the e-newsletters that come out every month as well.
Yeah.
So back numbers.
I was just looking through those newsletters today and I was very impressed. I might have to sign up.
Thank you.
Okay. Next question. This one comes from Gregory Donahue, who asks, is lithium always a hallmark of all young stellar object types?
It's a hallmark of T Tauri stars. Whether you find it in the higher mass objects, I'm not sure. I wouldn't have thought so because they're more numerous and thus hotter. So the lithium, if it is there, is going to be destroyed much more quickly.
Okay, interesting. And I would like to add on to Gregory's question, because I've heard about how lithium is a indication of a star being particularly young. Why is that?
Oh, sorry. Yeah, that's because lithium is destroyed at high temperatures. So once the star kind of turns on, if you like, once it actually becomes a star, i.e., it's fusing hydrogen in its core, that's too hot for lithium to survive. And the atoms are kind of pulled apart. So no more lithium. I mean, you do get a certain amount, because obviously it takes a long while for the entire corpus of lithium to be destroyed. But generally, the less lithium you find, the older the star is. And conversely, the more you find, the younger it is.
Interesting. Thank you. All right. This next question comes from Yogesh, who asks if stars like pulsating variables are periodically expanding and contracting, does the atmosphere then change, or does it remain the same?
These aren't pulsating variables. They don't pulsate at all. Any variables that are pulsating are going to be a lot older.
Okay. Interesting. Thank you.
I mean, things like Cepheid variables, Miras stars, Betelgeuse. Betelgeuse is a very good example. It's a very old star. We're talking about the other end of the age frame. So no, very young stars, at least as far as I know, don't pulsate. Or if they do, they don't pulsate for the same reason.
Right. And just to add a comment for Yogesh, my answer to that in the sense of old stars, not young stars like we're talking about here, would be yes, the atmosphere does change because it's getting less dense and cooler typically as the star is expanding. So there is that change that you can see. But it is a little off topic. So we're going to go back to young stellar objects now.
It's about variable stars.
All right. Next question here comes from Timothy Weaver, who's asking about the lithium phenomena. Timothy asks, by destroy, do you mean that the lithium is fused? And if the lithium is being destroyed by fusion, does this also mean that deuterium is fused?
My honest answer to that is I'm not sure. I'd rather say that than try and sort of think out the box. I think what does tend to happen is because all these young stars rotate very quickly, which tends to mix up the elements in the atmosphere. So the lithium, which originally is going to be at the very kind of outer edge of the atmosphere, which is why we see it in absorption. Okay, because the light of the star has to come through the lithium.
Right.
Because it starts off in the outer layers of the star, and also probably in the circumstellar disk as well. Because don't forget, we've got lots of lithium on Earth. Yeah, because Earth isn't hot enough to destroy it. Yes, I'm not exactly sure what happens to the lithium. I think it is fused, if memory serves me correctly. Yeah.
Okay, thank you. And more on the topic of lithium and its abundance here on Earth, Michael Gardner would like to know if the Earth's small amount of lithium came from the early or young sun during its T-Tauri phase.
Yes, it probably would have come out of the sun's circumstellar disk, which is more or less where everything on Earth would have come from anyway. So that circumstellar disk would have contained lithium. And as the Earth, if you think of those pictures we've seen of young stars with sort of multiple rings, those rings are there because forming planets are sweeping the material up. So they're making holes in the solid circumstellar disk, if you like. So as the Earth went along and accrued all that material, some of that material would have been lithium, yeah. And of course, it's not hot enough on the Earth to destroy it, which is why we've still got lithium for our batteries, for our electronic cars.
There you go. All right, thank you. Next question. This one is from Gregory Donahue again. He asks, for the larger Hades YSOs that do not have disks, is it thought that since they are hotter A types, their UV light has stripped away the material?
Yeah, I think there's a certain amount of that going on. Yeah, it's not that they don't have disks. It's rather that they're not necessarily associated with gaseous nebulae. I think possibly the reason is because they have accrued more mass. They've basically sort of sucked the nebula material in, if you like, to actually form the star, which might be one reason, why we don't see them attended by nebula.
Okay, that makes sense.
Some of them probably are, but there are quite a lot of these objects, and they're a fairly sort of homogeneous group of stars. So I'm not making great sort of sweeping generalizations, but it's kind of true as a kind of a vade mecum sort of thing, as a rule, rather than across the board.
Okay, thank you. All right, and our next question comes from Jay Miller, who asks, in these stars that have polar outflows, what would we see if the pole is facing us?
Oh, that's very interesting. I actually observed one of these stars. It's called V1331 Cygni, and we do see it pole on. And as you would probably expect, it doesn't vary very much, because most of the causes of significant variation is probably due to the angle that we're looking at the circumstellar disk. It's a slightly misleading term, disk, because when you say disk, people think of a frisbee or a fried egg or something like that. Near the star, yes, they are fairly thin and sort of disk-like. But as you get further away from the star, at the outer edges, you have what's called flared disks. So they're a bit thicker at the edges. Because otherwise, every time you've got a deep fade, the star would have to be, exactly equator on, and obviously that's not going to happen in the amount of cases where we actually see that happening. So because you have a flared disk, the star, it doesn't have to be at 90 degrees. It can be between sort of 60 and 90 degrees inclination. But in the case of V1331 Cygni, where we're looking down at the pole, we don't see any of the star, eclipsed by that circumstellar material. So we don't see deep fades. We see very little variation. I mean, most of the time I've looked at it, it's been between about magnitudes 12 and 12.7. Doesn't normally go outside those limits, because the changes in light we see, are fairly gentle.
Mm-hmm.
But it's still worth keeping an eye on just in case, because these things always surprise us.
That's the truth. All right, thank you. And so speaking of that tangentially, Mark Spearman has a question here about RW Aurigae. He says that it looks like it's brightening now, but that the variance is huge. So is that variation as seen in the AAVSO light curve accurate?
Yes, it probably is. I have an old book that was given to me many years ago. I think I might even still have been at school, by a member of the BAA. It's called The Story of Variable Stars. It's the best book on variable stars that's ever been written, and it was actually written by people at AAVSO, and it has a mention of RW Aurigae in there. I'm quoting from memory now, so this might not be exact, but it says words to the effect that RW Aurigae varies so rapidly that it's been difficult to give it a period. So obviously, I think this book was written in about 1948 or something like that, just after the Second World War, I believe. So obviously, at that time, it was varying an awful lot. So yes, I think the observations are correct. They do on cursory examination. They do look like there's a lot of scatter going on, but that's only because the time frame has been compressed. So yes, it does vary quite quickly.
Very cool. Thank you.
Plus, I don't think Joey Rodriguez would have used it in his paper, you know, if he thought there were suspect observations there. He's a professional astronomer.
Got it. Okay, so next question here comes from Roger Ben, who has asked if there are any specific polarimetric studies which have been done on these variable stars so that maybe the characteristics could be refined further.
Yes, in fact, they have been done on both RW and SU already, as well as several others. Something I didn't mention with some of the Habe stars is after they've faded, their colours can become more blue. You know, if you use multi-wavelength observations, you'll see that just after they've passed their minima, the star becomes bluer, and the reason is because we are now getting polarized light off the inner edge of the circumstellar disk, and that scattered light. Obviously, blue light has a, you know, it's very high frequency, so that gets scattered easily, which is in fact the same reason the sky is blue. Scatters, you know, it scatters the light, and this is what we get in some of these Habe stars. It's also worth pointing out that I mentioned you've got your T Tauri up to about 2 times the mass of the sun, and you've got the Habes up to about 8 times the mass of the sun. Any star more massive than that doesn't actually go through the sort of YSO phase as such at all. It's simply too massive and too energetic. It moves so quickly onto the main sequence, you know, that we basically don't really see it as a YSO, as you know, as I've been talking about. So that's why we don't get YSOs over 8 solar masses. We obviously get them, we just don't detect them as such.
Interesting. It's good to know.
They kind of cut out the middleman, if you like. They just go straight from one to the other.
Thanks. Okay, let's see. We've got a couple questions about spectra next. So first of all, Kevin Gurney asks if YSOs have strong emission lines in their spectra. If so, what wavelengths?
Actually, I might pass that one on to you, because you're the spectral expert, aren't you?
Oh boy. Well, I've never shot a YSO before. I'll tell you what, I'll get back to you on that. I got my spectra atlas next to me. I can peek in while you're answering a different question.
I think the disk is a certain contributor to that.
Okay. Yeah, I feel like I've seen spectra with big emission lines in them that were labeled as YSOs, but since I've never shot any myself, I can't say for sure, how common that is or anything like that.
But it is one of the things that does tend to characterize it. Yeah.
Okay, cool. All right, and next question, spectroscopy wise, is which class of YSOs has the strongest spectral variation?
Oh, it's. I'm not hedging the question. It's slightly difficult to say because we don't just get the spectrum of the star. We get this, we get a contribution from the circumstellar disk as well. So that's a slightly more kind of complicated issue. But again, you can have that one.
Oh boy. Yeah, I don't know. Maybe I'll find out from my spectral atlas in a minute.
I think this is called passing the buck, isn't it?
I think so. I think that's the right word for it. Okay. So next question here. This one's from Gregory Donahue, who asks, what type and size of telescope do you use for T Tauri observations? Gregory says that he has an 8-inch SCT, and he'd like to know if he can use that for these stars.
Oh, yes, he certainly can. I mean, you'll be able to see. Well, I mean, the amount of stars you can probably see is probably going to be in three figures. They're not all faint. For instance, T Tauri itself never really gets much fainter than sort of 11th magnitude. T Orionis is another one, right in the Orion Nebula. RW Aurigae gets, you know, apart from those really, really faint bits, normally goes between magnitudes 10 and 12. You know, they're all well within the range of a 8-inch SCT. And in fact, that star I was talking about earlier, the really, really weird one, which is V347 Aurigae, with the strange outbursts that haven't really been sort of anything like it, hasn't been seen before. I believe those outbursts were to about magnitude 11. So again, that's well within the range. Yeah, I mean, you know, you can do original work on these stars with, you know, nothing more than something like that. So yeah, more than adequate.
Excellent. That's good news. I also, before this webinar, thought that YSOs were mostly very faint, which is why I haven't shot any spectroscopically so far, but I'm seeing that I'm going to need to change that pretty soon.
Yes. Oh, yeah.
Speaking of, I have just found the answer to the question about emission lines, and I pulled out my copy of Walker's Spectral Atlas from the shelf next to me, and I can see that there are indeed very strong emission lines in these reference spectra of R. monoceros and T. Tauri, and they're mostly hydrogen, but there are some emissions from like forbidden oxygen and iron, so that's super cool. And Walker's Spectral Atlas, by the way, is available online as a PDF, an earlier version of it. Just Google Walker's Spectral Atlas for amateur astronomers, and you can reference the same spectra I'm looking at. So that's my answer to that question.
Okay, thank you. Bailed me out.
All right, and I'm going to check for questions on our Facebook live stream. Let's see. No new questions on Facebook, although we do have a thank you from Harold Luck, who says that, thank you, Michael, you have given me fuel for my night sky observations.
Excellent, excellent.
All right, so next question here, it looks like is from France Joseph Hampsh, who asks, what does the brightness factor mean on your webpage?
That's just a general guide. You know, it's nothing scientific. You know, it's just really kind of based on the equipment you've got. Like the chap with the 8-inch SCT, you know, he's not going to want to look at sort of 14, 15, 16 magnitude stars.
Mm-hmm.
But you know, if he just picks one of the, I think there's only about sort of three categories there, sort of bright, medium, faint. So, you know, if you've got a small telescope, you're not going to pick the faint one. You're going to go for one of the other two. And that will just sort of bring up a list of stars that I, in my infinite wisdom, have deemed to either be bright or medium or faint.
All right, thank you.
It's just a general guide.
Yeah, that's useful. So the next question here comes from Jamie Jenkins, who says that he's briefly looked at the target list for YSOs and saw that the recommended cadence was 1 day between each observation. Is that pretty much the standard recommendation for YSOs?
Yes, it is. In fact, some of the very active ones, I'm thinking of RR Tauri here, which varies between about magnitude 10 to 14. It's completely unpredictable. It's very rapid, sometimes 2 observations a night. Virtually in the same field, you've got an even more rapid one, which is bright, almost binocular bright, which is CQ Tauri. Very, very interesting, very irregular, and very, very rapid. I actually saw this one. I actually saw it vary as I was looking at it.
Wow.
It dipped by about, well, it dipped by almost a magnitude within the space of a minute.
What? That's crazy.
That's how rapid you're talking about. I haven't seen it since, but it you know, it still varies literally from one night to the next.
Wow. Well,
those 2 stars are very, very close together in the sky.
I know what's going on my observing list. Wow. All right, and that was CQ Tauri was the one you said that was so fast?
Yeah, the very fast one. Yeah.
Cool. Okay. That's somewhat related to our next question here, which comes from Rabi Mukherjee. Apologies for mispronouncing your name. I'm sure I must have. Who asks, what is a good YSO to start with?
Oh,
Observing.
definitely that one. Yes.
Okay, great.
But no, I would say something like, T Tauri is okay. So say, it doesn't normally do anything fabulously exciting. But that's a good one to start with. Let me have a think. There's quite a few in Cepheus. Cepheus is wonderful for these things. Of course, there are huge star formation areas there. BO Cephi is a good one. It's one of these sort of dippers that have. In fact, when it was first discovered, they thought it was an algol variable because it had these algol-like dips. That's a very, very good one. That's usually between magnitudes sort of 10 and 12. So again, not fabulously faint. There's one not far away, which is BH CPI, which is actually a little bit brighter. Yeah, I mean, just kind of look on the webpage, at bright or medium variables, and there'll be a whole list there. So just take your pick.
Great, thank you. Could you repeat the designations of those two stars, please?
Oh, one there's BO CPI.
Okay.
And the other one is BH.
BO and BH, and that's B as in beta?
Yes.
Cool.
BO as in body odor.
Okay. Okay, next question. So which stars, do you have a few stars which you wish that more visual observers would focus on?
Well, all of them, I suppose. Well, like in that episode with that strange star V347 Auriga, when John saw it rise, he sent me an email, and as soon as I got the email, because it's not really been sort of known before for that type of star to rise like that. I sent an email to HQ. They issued an alert on the same day, and lo and behold, lots of people started observing it. So we now have a very good light curve of that outburst, and not just in visual, in a range of wavelengths as well. Because obviously, the more wavelengths you can get, the more you can find out about what's going on. So yes, I mean, just kind of pick a star, really. I suppose some of them do tend to be over observed. Something like T Tauri, yes, you can observe it every clear night, from one night to the next. But the chances are it's not going to be doing anything. They're very extreme. So, but by all means, say for instance, if I take T Tauri as an example, by all means, have a look at it every night. You don't necessarily have to make an estimate every night, because you might look at it on sort of night one and it's 9.5. Yeah, you might look at it on sort of night two and it's still 9.5. But then you might look at it on 9.3 and it might be down to magnitude 11 again. Not very likely, but it might be. So it's always worthwhile following it. Certainly the sort of quicker ones are better, obviously, simply for that reason, because they're always doing something. RR and CQ Tauri, those two, they just go together very well. Yes, I mean, RR Tauri is a good one. It's also a strong source of X-rays as well. So there's all sorts of interesting stuff going on around RR Tauri, and it's got a little nebula associated with it. It's kind of got everything really.
Cool. Yeah, well, that's
like, yeah, I mean, its light curve looks really, really weird. If it was a patient, he would have died ages ago. Temperatures going up and down like no one's business.
Well, it's definitely going on my observing list, and I doubt that I'm the only person in the audience thinking that.
Yeah, it's a good. It's good. You always get bang for your buck with that one.
Okay. Let's see. Next question. Do you have any recommendations for observing young stellar objects in light polluted areas such as Los Angeles?
Oh dear. Ooh, well, I mean, apart from going for the bright ones, it's a bit difficult to know what to say, really. Um, not living in LA. I'm actually quite sort of rural here. I don't really. It's hard to say.
Mhm.
Well, one slight advantage of them is sometimes it's hard to observe red variables from light polluted areas because it kind of it plays havoc with the color response either of your eye. Of course, I'm purely a visual observer, so I'm just talking from that sort of viewpoint really. Yeah, it can play havoc with what red stars look like to the eye if if you've got a light polluted background. The great advantage of a lot of YSOs is they are not red stars. They're
Mhm.
quite white, a lot of the time.
Okay.
Just yes, I've just seen a question here about NSV 87 and 93. These are two NSV objects. They're in Cassiopeia. They're in a star formation region in Cassiopeia. I think I'm responsible for them actually, because at the time they were possible YSOs. It's I think if you ask if you ask Sebastian, who runs VSX, he'll probably tell you that they are not YSOs. So they're probably not worth following. But there are a couple of actual YSOs in the same area, but they are not there.
Interesting. Thank you. And just to restate the question for those watching on Facebook, the question was about why NSV 87 and NSV 93 have not been observed in 10 or 11 months, and why aren't they being observed more often? And so that was a good answer. Thank you, Michael.
That doesn't, but by all means, if you want to continue to observe them, do. But apparently they are not YSOs. So
Okay.
Rules the bit.
Interesting. Thank you. All right. Next question. So this one goes back to the question about light pollution, and I think it's a really important one. Bert Watson has asked if any filters are useful for making observations.
Well, John Pickett, who I was talking about earlier, who's the guy who discovered the outburst of B347 Aurigae, he uses I can't remember what filter he uses. It's not one of the standard ones. In fact, I don't even know if he's here today. If he's here, I'll tell you. It's a sort of pan RGB sort of filter. I think it's called TG or something like that. As I said, I am purely a visual observer, so I don't really have anything to do with filters. But certainly, as I was saying earlier about the stars bluing, sometimes after they've faded to minimum. Obviously, the sort of wider wavelength brackets you can get, the better. But the blue, especially in their cases. But yeah, I mean, basically, it comes down to a nice wide range. That's the important bit. As we saw in that, the Bessie Aurigae, where the sort of visual minimum is very, very deep. But in fact, in the far infrared, it's not a minimum at all. It's a mini maximum. So that gives you a really good idea as to what is going on in the environment.
Interesting. Thank you. And could you add to that some comments on filters for visual observing? Are those a good idea?
I believe. Well, I presume if you're going to be doing the visual observing, you'll be using a visual filter.
Okay. So as far as I know, I'm gonna add a comment here, just based on what I know out of like the AAVSO's visual observing manual. As far as I know, visual observations are supposed to be made unfiltered for standardizing. I asked that question because I know that we get a lot of people asking about light pollution filters and whether they should be used for visual observing, but the answer is no, as far as I'm aware.
Yeah, sorry, when I said visual, I meant V. Sorry.
Ah, gotcha.
Yeah.
Yeah, so for visual with an eyepiece, then I assume you wouldn't recommend using a filter on the eyepiece.
Oh no, just just straightforward eye.
Okay.
As I do.
All right, thanks. Yeah, it's good to restate that. That's one of the most common questions that we get here at the AAVSO is about whether you should use a light pollution filter when you're making your visual observations. So
I think as long as you're consistent,
Mhm.
as long as you use it all the time. But then again, it it depends. It depends what it's passing through. It ideally it would be compatible with one of the standard filters.
Yeah, you'd probably. I can't think of a way that you would make a filter that enhances contrast while also not potentially throwing off the balance with the comparison star, because they might have different spectra.
Yes, exactly.
Hmm.
So I would say sort of eye or not at all. If that's what if that's the road you want to go down.
Yeah. Okay. Oh, John Pickett is here in the audience, and he has a comment. He says that he's a DSLR observer and that he reports tricolor green as his filter.
Ah, TG, that's right. Yeah. Cheers, John.
Okay. So Roger Venn has a question here about T Tauri. He says that T Tauri has a BV value of about 1, B minus V value. So is this value comparable to other T Tauri stars? And are there any particular issues when observing these T Tauri stars visually due to their redness, like the Purkinje effect?
They're not usually red enough for that, even though they have what is sometimes considered to be a sort of a red type spectrum, sort of spectrum type N. They are not actually usually terribly red. I think the BV of 1 is probably about right for most.
Okay, thank you. And next question here. Actually, this is a comment from Jamie Jenkins, who says, I've been moderately active in long period variable photometry during the last several years, and I'm not set up for time sequence photometry. However, Michael has made YSO observations seem to be the next step for me in the coming months. Thank you, Mr. Poxen. Great job.
My job, my mission here is complete.
Okay. This next question comes from Sergey Host, who asks, what telescope and observation method do you use?
Me? Oh, purely visual. On a half-meter telescope, just Dobsonian mounted. I don't have go-to. I don't have anything. Perfectly manual and eye. I mean, you can't actually get more. You can't get more basic than that, really, can you? Mm-hmm. I also use a bit of. I've written myself an app which brings up charts and you enter the magnitude and everything is basically recorded and it's output as an AAVSO format file. But in terms of observation, just eye and scope, absolutely nothing else.
Okay, thank you. And that sounds like
you sort of need to know the sky pretty well to do that. That's the downside. It's just more fun than go to.
I'm inclined to agree. That's the same way that I observe.
Quite right.
Okay. Next question. And this one's also from Sergey Host, who asks, in view of rapid fluctuation, like in CQ Tauri, is continuous photometric monitoring over the course of a few hours relevant?
Yes, certainly in some of the more active stars, like that one, and also like RR Tauri as well. Yes, it is. Yeah. On the more slowly varying ones, like T Tauri itself, probably not. But again, there might be the sort of small variations that might be due to star spotting. This is certainly the case with a lot of the fairly sort of low amplitude T Tauri stars. For instance, there's one actually near V730 CPI, which I was looking at earlier, the magnitude 12 to 16 with a very 15.7 magnitude minimum, that one. There's another style very close to that called DI CPI, as in detective inspector. Its range is said to be about 11.9 to 13.5, I believe. In practice, it stays at roughly 11.9 visually, but that's only because, you know, I'm observing it visually. If you were to use a CCD on it, you might well see variation due to something like star spotting. So it's kind of horses for courses.
Okay, interesting. Thank you. And on that topic, could you just summarize which types of YSO variability are best for a visual observer to focus on?
Yes, I mean, generally anything with an amplitude greater than half a magnitude, and anything less than that, you can still see variation. But I would say any star with an amplitude less than half a magnitude is probably best followed by, you know, CCD or something like that. Anything greater than half a magnitude, you know, I was going to say the world is your oyster, but it's, you know, the galaxy is your oyster.
All right. And speaking of the amplitudes, is VSX the best source for amplitudes, or is it up to date on some of these erratic YSOs?
VSX is about as up to date, I think, as you can possibly get. Yeah.
Okay, wonderful.
In fact, I check it myself regularly, because one other factor that I haven't mentioned about all these stars is that they're a very diverse group, and it's quite possible that some of them might turn out not to be YSOs at all. In fact, that's what happened with those two NSV stars, NSV 87 and NSV 93. I think I popped over to VSX one day and had to look for them, and they weren't in the YSO group. They were semi-regular variables or something. So yes, it's updated very, very quickly, very, very well. So lots of thanks to Sebastian Otero for that. He does a fabulous job.
I'll second that. And oh, this seems like a good opportunity to plug Sebastian's webinar. That's on our YouTube channel. He gave a webinar earlier this year all about VSX and how to use it effectively as an end user. So if you are watching this webinar and you did not catch that one, it could be worth checking it out to optimize your searches for YSOs. Okay, this is the last call for questions on Zoom. I'm going to go ahead and check for questions on Facebook while you guys are typing. Okay, no questions here on Facebook, and looks like no more here on Zoom. So I'm going to go ahead and put up our closing screen here. All right, there we go. So first closing announcement is the most important by far, and that is that I would like to extend a huge thank you to Michael Poxen for sharing his time and knowledge with us today. Thanks for a wonderful presentation.
My pleasure.
I would also like to thank again our sponsors, DC3 Dreams and Voice Astro. DC3 Dreams provides high-end observatory automation and web-based multi-user remote imaging. The AAVSO net observatories use DC3 Dreams ACP Expert for the Bright Star monitors and other programs. The AAVSO Photometric All Sky Survey project, also known as APAS, has used ACP Expert's AI scheduler to automatically acquire over 500,000 SAR fields, hands-off, at a rate of 1,000 square degrees per night. This has resulted in photometry for over 128 million objects in about 99% of the sky. The Boyce Research Initiative and Education Foundation provides online astronomy education, observatory resources, and research experiences to students, student teams, and schools in order to learn how to perform observations, conduct research, and publish their results in scientific journals, such as the Journal of the AAVSO. Today's how-to hour has been recorded, and right this very moment, you can find the recording on our Facebook page. Before too long, it will also be uploaded to our YouTube channel. If you enjoyed today's broadcast, you would probably enjoy watching some of the recordings of our past webinars. They covered topics such as circumstellar disks, star spots, and accretion. You can find those recordings on our YouTube channel as well. And if you like what you see there, please do consider subscribing to our channel. It only takes one single click, and by doing so, you will be helping us to increase our educational reach. YouTube will be that much more likely to suggest our videos to others. That's just one more way that you can help support the AAVSO. Speaking of support, this webinar series is being supported by you, the viewer. So if you're not a member, I highly recommend that you join the AAVSO. AAVSO membership comes with a huge amount of benefits, including access to our mentorship program, where you can learn more about either visual observing or photometry, or even spectroscopy with a mentor, one of our experts. We also have a remote telescope network, which would be put to great use by observing some of these young stellar objects. We have a large telescope in the southern hemisphere with a shell spectrograph on it, and I can't guarantee anything, but if you put in a proposal asking to observe some young stellar objects with it, I bet you'll get approved. And as always, we would be so grateful if you would consider donating to the AAVSO. Every single donation matters and goes towards keeping programs like this one alive.